speech, because I think what's been lacking in this country is a systematic scientific network to look at problems of climate change and global warming from a scientific perspective. And that was my idea, that we set up an Indian IPCC. So I got about 250 scientists, 100 institutions, put them together and start thinking about problems and models from an Indian perspective. Some success we had. Unfortunately, that could not get sustained. One of the problems with the Indian academics is that if you give them the choice of publish or perish, they would rather perish. And to get them to publish has been one of the biggest problems I had as minister. There's a lot of knowledge here, Professor, but getting that knowledge out into the published domain and subject it to a peer review is something that is an anathema to the Indian scientific community, with due respect to the president of the Indian National Science Academy who is sitting in front of me. So I am looking forward to your lecture. It may appear to be very futuristic, but I think we need to listen to voices like Professor Shu, who come to this with impeccable academic credentials, no political agenda, but just formidable scholarship. So I suppose he'll speak for about 45 minutes?
Yeah.
You have about 45 minutes, and then we'll throw it open for questions and answers. So the floor is yours. You want to speak from here? You want to speak from here?
Okay. Thank you. Thank you. Very honored to be here in India. The introducers did convey the central message I hope to give tonight, which is that it's possible actually to make money solving climate change, all right? Moreover, India, I think, is the best position to do the two kinds of things that I think need doing. One is to halt climate change, stop emitting CO2, and then the other is to use a safe, proven method of extracting carbon dioxide out of the atmosphere, basically by plants. Plants have been engineered by evolution to do this. And then we need to do something with the vegetation, of which India has a tremendous amount. So I'll talk first about climate mitigation goals and objectives so that we can see where we're going. And then I'll talk about how to restore atmospheric carbon dioxide to a safe level by the end of this century. So it's futuristic, but not something that is too far above, beyond the horizon. Then I'll talk about the optimum nuclear technology, which India is leading the world in, which is thorium nuclear reactors, and discuss 4 attributes of any nuclear technology to gain acceptance by the general public. I call them the 4 S's, that it's sustainable, that it's secure, that it's superior with a $, meaning it's actually cheaper to use it than any other form of clean energy, and even fossil fuels, and ultimately that it's safe. And then I'll talk about in detail the idea of carbonization of biomass, which we call supertorrefaction. And as a byproduct, liquids as well as gases, I won't talk about that. I'll talk about the solid product, which is basically charcoal, or if you make very fine charcoal, activated carbon, which India actually supplies half the world's supply. But instead of taking the 2 weeks that the conventional method uses, we can do it in 1 minute. Okay, so I hope that's kind of a preview of what we're going. Finally, the production of this biocarbon can give negative carbon emission. All right, and we'll see what that means. Okay, so this first slide says where we're going and what the result must be if we're to get down to safe levels. Now, many people believe that the safe concentration of carbon dioxide is 350 parts per million, which we passed in 1988. That's a global average, all right? And it's been steadily climbing until today. It's 407 parts per million. And if everybody lives up to the so-called commitments made in Paris at COP21, this should turn over. Even though it's climbing this way, the commitments, if they're met, would turn it over until it's about 450 at mid-century. Beyond that, it's believed to be unsafe. In fact, many people think 450 is too low, that if we stay at 450, then business as usual, the end of the century, the temperature would rise by 3 or 4 degrees, exceeding the 2 degrees that's considered acceptable and the 1.5 degrees that's considered desirable. In Asia Pacific, it would probably be more like 6 degrees C. So just imagine the average temperature in summer being 6 degrees Celsius higher than it is today. It would be almost unlivable in India, okay? And if you look at a really long time scale, then eventually all the ice in the poles, including Antarctica, would melt, and you would have 60 meters of sea rise. So this is clearly, we hope, not in our future or in our children's future or great-grandchildren or whatever. Now, the IEA, the International Energy Association, has estimated what it will cost in US dollars, in trillion US dollars, to reach the first stage of this plan, namely to get to that red point, which would already exceed what we can project as, reaching this possible catastrophic turning point, all right? It would cost roughly 13.5 trillion US dollars by the governments of the world, and the fossil fuel industry would have to invest 68 trillion US dollars in efficiencies and carbon capture and sequestration to capture the carbon dioxide that comes out from thermal power plants. I'm going to go out on a limb and say, if one adopts the two molten salt technologies I'm talking about, then it will only cost $6 trillion to build the nuclear reactors, the version that most scientists agree is probably the best and safest that you can build, which are 2 fluid molten salt breeder reactors running on a thorium fuel cycle, plus another $10 trillion for the supertorrefaction. All right? And that would flatten, the nuclear reactors would flatten this curve so that you don't cross a 450. And the second technology would bring it down. Now, how does it bring it down? Well, these are the measurements made by San Diego scientists, by Keeling and his son, who measured carbon dioxide directly from the peak of Mauna Loa in Hawaii. So right away, the first year, they saw that the carbon dioxide level goes up in the fall when plants begin to die and decay and put the carbon in them back into the atmosphere as carbon dioxide, as bacteria decay it. And then in the spring, as new plants, vegetation grow, it comes back down. And the up and down is about 8 parts per million, okay? However, in addition, there's a steady drift upwards, which comes from our burning fossil fuels. So if one can stop this upward climb over here, so it flattens out with good energy technology, then in principle, you're 100 parts per million above 350, which is considered safe. So if you could carbonize all the vegetation that dies before it decays, then you would only have downs. You would never go back up in the fall because you've carbonized it. You put it in a form which does not decay. If you have a bag of garbage, it decays in a day, but if you have a bag of charcoal, it could last 1,000,000 years without decaying. So you've sequestered it. Okay? At 8 parts per million, per year, how long would it take to go down by 100 parts per million? It would take 12 and a half years. Okay? So in principle, if you were really ambitious, we could solve climate change in 12 and a half years. Of course, it's almost impossible to find every blade of grass that died and carbonize it. What can you do? Well, 10% is certainly possible because 10% is what undeveloped countries in the world do in burning wood. So if you just stop burning that wood, instead made it into charcoal, it would be 10%. I think that 25% is reasonable. Okay, at 25% means you're going 4 times less fast than maximum. So instead of taking 12 and a half years, it would only take 50 years to come down to where it's safe. That's basically the outline of the talk and the hope. Could you? Oh, sorry. I'm sorry. Okay. Now the first part, I don't really need to explain. Dr. Homi Bhabha of India in 1954 in a presentation at a conference attended by Prime Minister Nehru already mapped out what India's goals should be in terms of utilizing nuclear energy and in particular thorium cycle to satisfy all of India's needs for 400 years. Okay, so very far-sighted. Beyond 400 years, you might have to do something different. Perhaps that's fusion. Perhaps it's something else that we have not yet discovered in science. Nevertheless, it was a 3-stage plan, which one was just to produce what is usually called nuclear waste, but he pointed out spent fuel is not waste, it's a resource. And that's a common theme in sustainability. That is, we must stop thinking of having waste and turn in a circular way waste into resource. So that waste, that spent nuclear fuel has in a plutonium, which has extra neutrons that can convert more material, if you have a thorium cycle, into something that is fissionable, all right? And then finally, the third stage is to build reactors that run on the product of this thorium cycle, which is technically uranium-233. The only change I would ask Indian scientists to consider, and I talked to the people at the BARC, gave them a detailed report of the proposal, is to skip the second step. Skip the step that requires what are called fast reactors and go directly to molten salt breeder reactors, which cannot produce as much plutonium as you need, but which one design can both do the conversion and to do the breeding, okay? And we're going to follow up